While Douglas is setting up, I'll read some of the introduction. Douglas Tomasi is a civil engineer, extensive background in environmental modeling and analysis. He earned a PhD in geodetics and geomatics at the Polytechnic Institute of Milan, and he holds a PE in Italy. And then since 2005, his company has opened a branch in Maryland, so he's been enjoying the United States. And he's also a member of a professional group in the LIDAR committee, and is also on the TRB committee AV030. So with that, Douglas is going to talk to us about his looking at the four-dimensional noise simulation and demonstration project. Go ahead.
Yes, thank you. So the last presentation has come at last. Eventually. And how long have I got? All right. Okay, just to help you better understand and bear with my bad English, I try to give you an overview structure of this presentation. We'll go over 4 parts. The first one of which being an overview of the study area and the long-term measurements we performed. The area is always in Maryland, on the Interstate 95, connecting Baltimore with Washington, D.C., which we just saw in the previous presentation. And in this area, we positioned 4 sound level meters, one of which was, I think I might, all right. Another device. All right. This one was above the barrier, and the other 3 were behind that barrier. The monitoring was performed with the 4 Type 1 integrated sound level meters, acquiring every half a second. We wanted a very detailed sound level. And as an additional data, we had every 30 seconds an integration of the of the octave. The survey duration was middle term was 1 week. Well, the microphones are commonly mounted on tripods and are thermally compensated, which is not very useful in spring time or in summer perhaps, but is very useful in winter time to help maintain the required accuracy throughout the survey. And in addition to that, there was an external data logger with an integrated microcontroller and GSM module, which allowed self-diagnosis, text messages, and so on in case the battery went low or the weather peak too high or too low, whatever. Okay, and well, field activities always reserve some kind of surprise, and I think that everyone here, at least me, I've got it so many times. Every time there is a different surprise. And this time here on field, for example, we had a calibrated microphone cable, which was only 10 feet long, and the barrier was much taller. So we had to invent this arrangement here, but fortunately we had a very resourceful people on field. Someone called him Cam MacGyver. Okay, back to the serious stuff. Here are the noise level above the barrier, of course, and the one is behind the barrier. As you see, in insertion loss is about 14 dB, which is quite good. Of course, there are some local effects, some dogs barking, and so on. We don't know every one of these spikes, but we know for sure this spike here was a guy yelling in the microphone. It was this tripod in my backyard here, and so it went actually higher. The octave look like this. We have a time sequence in this axis. In y-axis we have the frequency, so that is the octaves, and in z we have the level. So they are acquired every 30 seconds because otherwise the data is simply too much, and this can give actually a very detailed overview anyway. Okay, further steps for this first part will be to give a hierarchical access to real-time web interface, which is something which we already do for airports, for example. In which case, the GPRS module is used to stream data continuously to the servers, and where they are analyzed and processed in real time. And okay, real-time model calibration is something we'll see in the next slides. And one further thing will be the GPS integration, which is not needed for knowing where the sound level meters are located, which is, of course, sound level meters don't have legs, fortunately, but to precisely align the whole network with up to 1 second, up to 100 of a second using the GPS time tags, which are very precise. As we know, GPS integration modules cost very little, so they are much more convenient than having other clocks installed on board and so on. Okay, this part I will skip it very fast over it. It's a description of an alternative physically based noise model, which takes into account some of the basic rules underlying the noise propagation. Noise can be observed either as a punctual or as a linear source. In this case, a punctual source emits, of course, a sphere, which is a noise sphere, which expands through space. And if we want to follow it, how it goes during time and in space, we have to divide it into pyramids. So basically tessellating the whole surface and following each of these pyramids. And we can imagine this. Every one of these pyramids represents a stream or a direction where sound travels or noise travels. And analyzing this direction, we can see if it hits a surface, which will be modeled with the correct material. So if it's absorptive or reflective, and so on. And from that, we can calculate the second order of pyramids which reflect, or in other ways, are partially reflected if the material is absorbed, and so on. Okay, for what concerns the source, the approach is similar to the one which was expressed yesterday, or 2 days ago, I don't remember. And we basically need to subdivide the highway, in this case, in many segments. Each of these segments will expand then in the appropriate number of lanes. And each of these lanes will have the correct number of tracks and light-duty vehicles on it, and the right speed, and the texture of the asphalt, and so on. Then we need also a 3D model as possible as accurate as for the terrain around the area, and of course also for the buildings, which are the main targets we are used to analyze. Okay, in this case we follow basically through all the emission sources and see what happens in the space. We normally see what happens in the space at every single sector. But what we are proposing here is to try a little different approach, which comes from an experience in gas emission dispersion, which uses this kind of approach which has been using this kind of visualization and analysis models for about 5 or 7 years. But before going into this, let me say that I sometimes wonder why we, as a community of technical people, of noise technical people, are we sticking with tools which are probably 20, if not 30 years old? Why are we only, okay, I mean, in the 70s, someone had idea and said, hey, how much noise do I get here at this window? And someone else said, okay, and this window, and this window. So they began a mapping of windows, so to say, or a mapping, and in the 80s, I think there was the spread of maps, of noise maps, contours, and so on. We are now in 2007, and we still use the same approach, which is more colorful because we have Google Earth and so on, which is more fancy and more accurate and everything, but it's still 2D. And we don't actually know what happens, or it's we know it, but it's not considered very often what happens in Z. And in this example here, there is the highway, there is of course a cross section, and we see that it's not to scale. The X and Y is not to scale. We see that the noise contours in cross sections have, of course, their own envelope, and the noise we get at the first store